In this video, I want to just go over the Mensink and Requate example that is provided in Lecture 10. In this example, the purpose of this example is to distinguish between the two different notions of option value, that is, that of Arrow, Fisher, and Hanneman and Henry, and the Dixit and Pindyke more standard approach. So the example that they use, consider a project, let's say a dam or a reservoir. The choices are to either not build in period 1 or build it in period 1. If you then you go to period 2, in which case if you haven't built it, you still have the additional choice of to build or to not build or to build. If you've built it, then you don't have any choices in period 2. But the payoffs in period 2 are uncertain. So you can either have theta lower bar, in which case the payoffs are low, only 10, or if theta upper bar, in which case the payoffs are high, which is 20. We're going to assume that the cost of building the dam is minus 18, whether you do that in the first period or the second period. So let's sort of walk through this example piece by piece. Consider first the case of open loop values in the second period. By open loop, we mean that decisions are made without knowing the information. So if you're in the second period and you're not going to be able to take advantage of the information and you haven't built, then you can either choose a payoff of 0, or you can get a positive payoff of 10 minus the cost of 18, which is a negative 8, or we can get a payoff of positive 20 and a minus 18, which is positive 2. If we assume a 50-50 chance of theta lower bar or theta upper bar, it's clearly better off to choose to not build. So the optimal choice, the open loop optimal choice in period 2 is to not build with a payoff of 0. If, on the other hand, you have built it in period 1, then there's no choice to be made. You got a 50% chance of getting a payoff of positive 10, 50% of negative 10, so that's a payoff in the second period of average payoff of 20. So the open loop, the payoff in period 2, if you've made the choice of D1 equals to 1, that is, you built it in period 1, is equal to 15. All right, we can now sort of tease this out. They use this notation of V tilde 0, 1 of D1 equals 0 if that is the payoff in period 1 following an open loop decision rule, in which you take D1 is equal to 0 is going to be a payoff of 0 in period 1 and a payoff of 0 in period 2, which we've already shown is what you're going to do if you haven't made the decision to build in period 1. On the other hand, the open loop decision rule, if you decide to build, or open loop payoff, if you decide to build, is equal to minus 1. So you get minus 8 or plus 2 minus 18, that's a minus 16 plus 15 minus 1 is the payoff of the open loop decision rule. You maximize over the 2, and we end up with an open loop payoff value of 0, which is associated with the decision rule, don't build, don't build. Now let's look at closed loop decision rules. In closed loop decision rules, you can actually see the information. You get information and then you act on that information. In this case, if you haven't built, there is a if you see that it's theta upper bar, then you're going to make this decision. You're going to take 20 minus 18. You're going to get a payoff of positive 2. If you see that you've got theta lower bar, you know you're going to lose money here, so you're actually going to choose this. So your decision rule is going to vary. If you see theta lower bar, you're going to choose to not build, payoff is 0. If you choose if you observe theta upper bar, you're going to choose to build with a payoff of plus 2. The expected value, 50-50, over those two payoffs is positive 1. in the if you've already built in period 1, then the closed loop decision rule is very simple. You're going to continue to operate with a payoff of 15, expected payoff of 15 in period 2. Now let's sort of go back now to period 1. Again, we're going to use this notation v tilde closed loop c d1 equals 0 is going to be equal to a payoff of positive 1. That is, you're going to get a payoff of 0 and then an expected payoff of positive 1 in period 2. Add those two together without discounting is going to give us a payoff of plus 1. V tilde c of d1 equals 1 is equal to, you're going to have minus 16 in the first period plus 15 in the second period. Add those together without discounting gives us a payoff of minus 1. So the closed loop decision rule is to not build in period 1, and then you may end up building in period 2, and that the value of that is positive 1. Okay. They finally introduce one additional notion, which they're going to call B upper bar of 1, which is to make a decision and stick with it. If you make a decision to build in period 1 and stick with it, the payoff of that is going to be minus 16 in the first period, plus 15 in the second period, or minus 1 overall. The B upper bar 0 is going to be don't get any payoff in the first period or the second period. That's going to have a payoff of 0. The maximum of across those two they call the net present value. That's the net present value of making a decision and sticking with it in period 0. The net present value is the maximum over that, which is going to be not build or a payoff of 0. All right, now they can get into the different concepts of option value. They show that the option value of Dixit and Pindyke is equal to the difference between the closed loop optimal, all right, where you would not build in the first period and then decide whether to build in the second period, minus the net present value, and that's equal to plus 1 minus 0. So the notion of option value, according to Dixit and Pindyke, is the difference between a decision rule in which you are going to be making your decisions after in the second period or in the future with new information versus the decision rule in which you make your decision without taking into account over the whole range of time your your information that you're going to have. All right, so that's the option value concept of Dixit and Pindyke. The option value concept of Arrow, Fisher, Henry is slightly different. It's the difference between the closed loop decision rule, in which you come to the second period and then you take into account that you're going to get the information, and the open loop decision in which you come to the second period and you don't have information. You can't take that information. It's the value of the information that you get in the future. So in this case, the Arrow, Fisher, Henry and the Dixit and Pindyke values are the same, but you can see that conceptually they're slightly different, right? In the Dixit and Pindyke case, we're comparing the net present value where you're making that decision and locking in on it. The Arrow, Fisher, Henry case is you are taking into account that you're going to get information and your choices might change. Okay. They finally introduce one other additional concept that is worth to sort of identifying here. It's helpful to see it graphically before you look at the math, and that is what they call pure postponement value, and that's the open loop value with making a decision of d1 equal to 0 versus d1 equal to 1. All right, so that's what they call pure postponement value, and that's just sort of the value of not taking into account the information, just that I'm actually going to wait for one period before I make my decision. Those are the concepts that are used in the derivation in Mensink and Requate, and hopefully this graphical presentation will make it easier to understand what's in the notes.